Alright, I'm not gonna lie. I had to stop the stream because I was kind of getting frustrated. I was having a hard time, I don't know. I was overthinking it. But what I ended up doing is I ended up creating the correct answer after a while of messing with it because one of the things that this website does not work with is I have to, every time I print some, I have to put the integers like this instead of like typically like in Python I can use these and put it within that and it works fine in Python, but for some reason the website's not taking that. So I had to redo that, but other than that, I finally figured out what I was doing wrong. And it's just, I mean, when I'm trying to find the average, I needed to stop trying to make such complex codes for this, and I just had to started having to think simple, like what would I do? And so to find the because all it's doing is finding the average every time, and between your highest and lowest numbers. And so if your highest number is 100, your lowest number is 0, then your first guess is the average of that. So you add them together divided by 2. That's the average. Now, I was overthinking this a lot, and I really should have just calmed down. And then all I did is, I mean, it's literally what he was doing earlier, but I was just overthinking it. And if the answer is too high, then you limit your height, the 100, to the answer. Because if that answer is too high, you know that that's the highest you can go. So you make that your new highest answer. And your lowest answer stays the same because you don't know how low it goes. So what I would do is every time I would receive an answer, I would turn that answer into either the highest or the lowest answer because you already know it can't go past that point. So, I mean, that's all I really had to do and just keep the equation, the highest plus the lowest divided by 2, and it'll guess in the middle of wherever the highest and lowest are. I don't know why I was overthinking it so much. It was giving me a headache, and I had to take a breather and just calm down a little bit because it was getting to me. And now I need some freaking headache medicine. It's so simple, but it's like when you're messing with all the codes, especially when he was talking about cubes and stuff, where it's a lot more going on. It just you get like a little mixed up, and you start thinking like way too complex on something that could be way simpler. And like if you look at how to make these codes, like there's so many different ways to make these codes. I mean, I'm sure there's probably a shorter, quicker way to do it than the way that I did it, but I finally got it. And after I got it, I mean, I had to stop and think of how my brain would work and what would I do if I'm trying to find the average. So it's not that hard when you just stop overthinking it. Floats and fractions. Every time you put this is on my notes. Every time you put a divide, it turns it into a float, and the only way you can get rid of that is you can turn your float, which is what I had to do on there too, because every time I was dividing, it was turning the number into a float. So to keep it from doing that, what I ended up doing is just putting that the answer is an integer on every loop. So it makes sure that when it comes up with the answer and it puts it in and it prints it out, that it's not putting it in decimal form, that it's strictly putting it as integer, no like 0.0 or nothing. And if you do that, if you take a decimal number and you put it in there and say it's an integer, then it gets rid of that decimal and turns it into an integer. It doesn't round it up or down. It just gets rid of the decimal. But yeah, that was a lot. Ugh. All right, here we go.
We've just seen an example of an algorithm that computes floating point numbers as an answer. And we've been playing with floats earlier on. I now want to take a little sidetrack to talk about floats and how they're represented inside the computer. And in particular to deal with something that you may have experienced earlier on in the course, where you'll get answers that'll give you some funny number where you're expecting 3.0 and it gives you 3.0000125 or something else. To deal with this, we need to go inside the machine for a second and talk about how floats represent real numbers. They certainly approximate them, but it's useful to get a sense of how the machine actually stores it, because it can't store an infinite number of decimal points or digits after the decimal point inside the machine. Here's the basic idea. Let's start with a decimal number, the numbers you're used to dealing with. The number 302 is really 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, or 1. It's 300 plus 0 tens plus 2 ones. Binary numbers, which is how the computer stores things, are actually represented the same way, but now in terms of powers of 2. So the number 10011 in binary is 1 times 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0, okay, which is actually 16 plus 2 plus 1, or 19, in decimal notation. Internally, the computer represents every number in binary, whether it's an integer or it's a float. How would we use that idea to think about how do we represent floating point numbers? Well, let's think about how we could convert a decimal integer into a binary representation, and then we'll do the fraction portion of it. So given a decimal integer, how would we convert it to binary? Well, let's take an example. My example would be the one I just had before. 19 in decimal is 10011 in binary. If I had 19 or anything that represents that number, how could I get it out? Well, what I can do is the following little trick. I can take the remainder of that number relative to 2. And that remainder actually gives me the last binary bit. It'll give me this bit right here, because that's the remainder that's left when I divide by 2. If I then take x and divide it by 2, integer-wise, using that double slash idea, all of the bits get shifted right. That is, x double divide by 2 is now 1 times 2 to the 3rd rather than 2 to the 4th, plus 0 times 2 squared rather than 2 to the 3rd, plus 0 times 2 to the 1 rather than 2 squared, plus 1 times 2 to the 0 rather than 2 to the 1. Or another way of saying it, notice I've taken these digits and just shifted them to the right. If I keep doing successive divisions like this, I can keep track of each of the bits that comes out, because the remainder gives me the next bit, and when I'm done with all of that, I've converted to binary form. So basic idea, given an integer, take the remainder with respect to 2, that's the low order bit, divide integer-wise by 2, shifts right, do the same thing until I've exhausted the entire integer representation. So here's a little piece of code that would do exactly that. Right? If the number's less than 0, I'm going to put on a flag that says it's negative, and I'm going to use the positive version of it by taking the absolute value of that number. Otherwise, I'm going to put in a flag that says it's not. And then I'm going to simply accumulate those results. If the number is equal to 0, it's just 0. That's pretty obvious. Otherwise, as long as the number is greater than 0, I'm going to do remainder, add that in, because that's the next bit into result, do the division to shift it to the right, and keep going. So if I look at that, here's a simple example of doing that conversion, converting decimal to binary. I'll start with a real simple example. If I start off with number as 3, and I do that computation, it didn't print anything, but the result is sitting in result. And there I get it. The binary representation of 3 is not surprisingly 1 plus 2. Let's just check to make sure I wasn't misleading you when I said 19 was, in fact, what I claimed it was. So if I make it 19, and I run it, and I look at result, it gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing. Let's take an example. 3/8 is 0.375, and in binary, that is 3 times 10 to the minus 1, plus 7 times 10 to the minus 2, plus 5 times 10 to the minus 3. It's just the digits associated with each of the placeholders. Here's the trick I'm going to play. If I can find a power of 2 big enough to convert all of that into a whole number, that is, multiply it by something so that it gets converted into a whole number, then I can convert that into binary. I just did that. I know how to do that. And then when I'm done, just divide by that same power of 2, and I've got a representation in binary of the fractional part of this number. In this case, I picked an easy example. 0.375, if I multiply it by 2 to the third, or 8, that's going to give me out 3 in decimal. I can then use what I just did as my trick to convert that to binary. That's 1, 1. And then I divide by 2 to the third, which simply says shift it right 3 points. And there is the binary representation of that decimal fraction. That's cool, right? It's a really neat idea. What am I doing? I'm using something I did for one computation, but converting another problem into the same problem. In this case, given a fraction, I'm saying find a power 2 that shifts it into an integer, use the same machinery, and then shift it back. And I'm simply taking advantage of
Yeah.
power.
What? You want a peanut butter and jelly sandwich? Alright. I'm gonna go ahead and
Or is
copy
it 2 because that's
this
simply moving?
because this is obviously something I need. The binary crap, this formula. All right. That's just to turn it into a positive if it's a negative. And then number is less than a 0, then it's negative, and turn it into a normal number, absolute, and else if negative is false. If number equals 0, while number is greater than 0, while number is greater than 0, result equals string number to 2% plus result I'll turn it back into a negative. And this is the binary formula. This is how you turn apparently numbers into. So if I run it, and a number like 9, number equals input. Okay, let's try this. It should be a number. Alright, let's try this. fine. Fine. Turn into a float. See what that does. Holy crap, okay. Not supported between instances of string and integer. Where is that at? If number is less than 0. Are you telling me that you can't input the number? What? I mean, I guess I could. This is so annoying. You know what? Here, we'll delete this. All right, delete that. Delete that. 9 here. Run it. See what that does. Ain't doing nothing. Oh, because you gotta print it. Hold on. God dang it. Zero.
Example. If I start off with number as 3 and I do that computation, it didn't print anything.
Hey, what's up, Tech Insider? Been working
there I
on
get
this
the
for
binary representation of 3
a
is
while,
not
trying to
surprisingly 1 plus 2.
log in.
Let's just check to make sure I
I'm
wasn't
in the beginning
misleading
stages
when
of
I said
this, so.
19 was, in fact, what I claimed it was. So if I make it 19 and I run it and I look at result,
So hard trying to think like a
gives me
computer.
back 10011, exactly as I said. All right, cool. So I can.
That's not what I got. What?
And I
Oh,
run
you.
it. And I
Wait.
look at
Oh, you. Hold on. No, wait. I gotta do results. Hold on. Print result. Do. There we go. Dang. Okay, so that's cool and all, but I don't understand why I can't do something like this. Like, why doesn't this work? Like, that's so lame. We're so lame. Because the greater or less than is not supported between instances of a string and an integer. But if I say that the number is an integer, okay. It's still a string, okay. Input, can I make it to where it makes this an integer? That's what I need. There it goes. That's what I needed right there. Just gotta put it in the right spot. Yes, okay, cool. That's what I was thinking. I was like, there's gotta be a way. Okay. Alright.
result gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing. Let's take an example. 3/8 is 0.375, and in binary, that is 3 times 10 to the minus 1 plus 7 times 10 to the minus 2, plus 5 times 10 to the minus 3. It's just the digits associated with each of the placeholders. Here's the trick I'm going to play. If I can find a power of 2 big enough to convert all of that into a whole number, that is, multiply it by something so that it gets converted into a whole number, then I can convert that into binary. I just did that. I know how to do that. And then when I'm done, just divide by that same power of 2, and I've got a representation in binary of the fractional part of this number. In this case, I picked an easy example. 0.375, if I multiply it by 2 to the third, or 8, that's going to give me out 3 in decimal. I can then use what I just did as my trick to convert that to binary. That's 1, 1. And then I divide by 2 to the third, which simply says shift it right 3 points. And there is the binary representation of that decimal fraction. That's cool, right? It's a really neat idea. What am I doing? I'm using something I did for one computation, but converting another problem into the same problem. In this case, given a fraction, I'm saying find a power 2 that shifts it into an integer, use the same machinery, and then shift it back. And I'm simply taking advantage of powers of 2 because that's simply moving the placeholder, if you like, for the decimal point, or I should say the binary point, in a binary representation. All right, there's code that'll do it. The binary point.
There's code that'll do it, but we don't need it to be complicating. I mean, there should be a way to do this, like... Oh, that's not what I meant to do. 0.375. It's going to say that's not. Okay. Now, that's obviously not going to work. The only way to make it. Oh, God dang it. Okay. Alright, let's try this. Okay, our fine. 375 came out. Okay. Well, I gotta remain this as an integer. That's the only way that's gonna work. And then I'm gonna have to do what? So you do what's 375? Oh. If you do 375, you get these numbers. If you have to move 375 over, what is it? 1, 2, 3 times, then all you do is move this over. 1, 2, 3. So this is your actual number. Let's see. All right. I want to see what he says about it.
Binary representation. All right. There's code that'll do it. I'm not going to walk through it. I'm going to let you look at it. I'm simply going to show you that this will actually convert a decimal to a binary fraction. So if I take this,
I got another one.
It. In this case, it says, give me a decimal between 0 and 1. Let's pick out a nice example. Let's start with the one that we had, which was 0.375. Sorry, let me make sure I'm here. And it says, oh, I'm going to tell you when I've gotten through it to get it up to something that is big enough, how many times I have to shift it over, what's the remainder, and there's the printed solution. Let's be daring and try another example I haven't tried before, just to make sure that it actually works.
Again,
we're going to call this out. It says, give me...
Hold up. No, it doesn't work with that one. Hold on. A decimal to binary. Let's say float. I actually want to rename this one now because that only works for integers. it's a binary. X equals floats. You know, input. Oh, it's gonna make me do all the work. Okay. I guess I use these. I don't know. Enter a decimal number. I don't know if I'll need this later, but I don't take any chances, so. P equals 0 while to the square root of P. This formula looks wild, bro. Who comes up with this crap? God dang. Times X. No. 1%? What is that? I don't even know if it does not equal 0. Then print remainder. This is a crazy formula, bro. Like, this is, man. String to, who comes up with this stuff? I swear. Integer. This is crazy. I need 2 parentheses. Hold up. 2. Square root of P times X with 3 parentheses. Oh my god. Huh? P plus equals 1. Number equal integer. Result. This formula's crazy, dude. Who comes up with this? What the heck? There ain't no way I come up with something like this. Oh my god. Jesus, am I supposed to be able to come up with crap like this? This is insane. Results equals 0 plus result. Oh, I did that one. Oh, it's period. My bad. Period. Dang it. Holy crap. Okay, that is some code. It's a bit ridiculous there. We have a unidentified name rum. That's no sir. Okay. What? Enter a decimal number between 3. Okay, so can I put 3 over 8? Probably not. Nope. Okay, so I'm gonna have to put 0.375. What? 0.375. Wow. Huh? I got nothing. What? Oh, I got a print result. Oh, hold on. Can I go ahead and... Okay. I'm playing around with all this. 0.375. 0.011. Whale.
A number between 0 and 1. And I don't know, let's take 0.333. And what do I get? Well, it goes through a whole lot more computation. It's telling me what the remainders are, but it's running through that computation, and it says the binary representation for 0.333 is this horrible looking mess you see on my computer screen down there. But the point of this is, now I can take any floating point number, convert it into something that can be represented inside of the machine in binary form, and use it. And that, by the way, is why you will occasionally see these strange things where you're expecting 3.0 back, and it has a little bit of an extra piece on it, because in binary it can get close to it, but not quite to the place it would like. But with that, we now have a way of understanding how we can represent floating point numbers inside a machine where everything is stored just in terms of binary bits. What are some of the implications of this? If there is no integer p, such that a power of 2 multiplied by x gives me a whole number, then the best I'm going to get is an internal representation that's close, which is why I won't get something exactly right. And obviously I'm only going to do this so many times before I run out of powers of p to use this. It also suggests that when you want to test equality of floats, you should be careful. You really don't want to given two floats x and y, you really don't want to use double equal sign, because it's going to check to see, is the binary representation exactly the same? It might not be. It might be really close. So we're always better off using the absolute value of the difference of two floating point numbers. Is it smaller than some small number, rather than using the more exact, are they exactly the same? And then finally, as I've already said, we may not always get an exact representation for a float in the way we would like, but if I do print of something, why does it always return what I'd expect, even if the representation isn't different? And the answer is because wonderfully the designers of Python designed it so that it would automatically round to the closest representation in terms of that floating point number. There are floats. Now we got ability to do integers and floats. We're in good shape.
True or false? Well, that was the whole point of that. The decimal 11 is what binary? This is kind of confusing, man. After me. I don't know. Okay, like I need to rewatch that because I obviously wasn't catching all that. This is kind of confusing.
We've just seen an example of an algorithm that computes floating point numbers as an answer. And we've been playing with floats earlier on. I now want to take a little sidetrack to talk about floats and how they're represented inside the computer. And in particular to deal with something that you may have experienced earlier on in the course, where you'll get answers that'll give you some funny number where you're expecting 3.0 and it gives you 3.0000125 or something else. To deal with this, we need to go inside the machine for a second and talk about how floats represent real numbers. They certainly approximate them, but it's useful to get a sense of how the machine actually stores it, because it can't store an infinite number of decimal points or digits after the decimal point inside the machine. Here's the basic idea. Let's start with a decimal number, the numbers you're used to dealing with. The number 302 is really 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, or 1. It's 300 plus 0 tens plus 2 ones. Binary numbers, which is how the computers store things, are actually represented the same way, but now in terms of powers of 2. So the number 10011 in binary is 1 times 2 to the 4th, plus 0 times 2 cubed, plus 0...
Sorry, I'm not trying to interrupt you there.
Oh.
Well, so the real estate thing, I'm stressing because it's like every time I make 2 steps forward, I get like 2 steps back.
Yeah.
I don't feel like I'm getting any traction. Good news, even though I have to retake that course again, I don't have to take the whole course, just to take the parts that are updated, and then it's just 4 more courses left to go, and they gave me extra handbooks and stuff and a certificate for the first 30 hours. So no matter what, when I go back, they're gonna give me a certificate every 30 hours, so I'll have the whole 180 when I'm done with my real estate class.
So they'll give you your hours?
Yes.
Well, that's good for something, right?
Yes, because it's 180 hours. The classes don't matter. I can fail all of them across the board as long as I make enough to pass, allegedly, so I have the 180 hours. It's the final exam that really matters. So there are a bunch of little mini exams, and that's why so many people were failing in the AYPO class or whatever.
Yeah.
Is because they weren't doing it right. So they had to reformat the whole thing to make it legal for Texas state legislature or whatever the fuck. And so they fixed it, but a lot of people are having to, redo it.
So they're trying to figure out a way where people don't have to go back.
And redo all the hours that they did.
By giving people the hours?
Yeah, so I'm still getting hours. I just gotta go and take that little quiz again. And then I got a couple of extra books and stuff that'll help me along the way. Plus, I get a cert for every time, because you're supposed to get a cert every time, and we just didn't. And so I would have had them already, but now because they didn't pass the Texas, I guess, part of it, they had to fix where they fucked up. In the process, they kind of screwed over a couple people, but, in the process of screwing me over, they made it easier for me, because I'm going to be honest with you, like, the passing rate was higher years ago when I first signed up for it, but then it started dropping dramatically because they didn't make it easy. But in the final exam, everything I'm looking up is not as hard as the one fucking school I signed up for. So I could have found, like, if I had did the other schools, then I would have already been done by now.
Are you trying to study, or?
Am I trying to study? Well, I'm going to print out my stuff first, and then I'm going to try to do some studying. I mean, the whole point is for me to finish it. I mean, it's not my fault that they fucked up.
No.
So I'm getting screwed over because they weren't doing the right stuff. But you can keep her studying. I should be fine. She's preoccupied with the little sing-alongs.
No, I just saw you moving around stuff. I didn't know if you're gonna...
Oh, I'm not studying in here, no. I'm gonna keep her preoccupied so you can have some peace. Because if we're both in here, then who knows what she's up to? Honestly, you know how she is.
Well,
Times 2 squared plus 0 times...
huh?
But it's good news, so
Yeah.
it's that.
I'm learning a way that you can see how the computer reads numbers.
Ooh.
Yeah. So, like, for example, the number 9 isn't the number 9 in the computer. The number 9 would be 1001.
1001.
Apparently.
1001. 1,000,100.
I don't know. This part's kind of weird, dude. Because he's talking about how the computer interprets numbers, and he's talking about floats, because floats are numbers that are decimal numbers, but they're not integers. Integers are whole numbers.
Okay.
So anything with a decimal is considered a float, and the reason is because floats aren't read the same as integers. It's weird, because computers don't have decimals; it's just ones and zeros.
Yep. No dashes.
Sorry, 1 times 2 to the 1 plus 1 times 2 to the 0. Okay, which is actually 16 plus 2 plus 1, or 19, in decimal notation. Internally, computer represents every number in binary, whether it's an integer or it's a float. How would we use that idea to think about how do we represent floating point numbers? Well, let's think about how we could convert a decimal integer into a binary representation, and then we'll do the fraction portion of it. So given a decimal integer, how would we convert it to binary? Well, let's take an example. My example would be the one I just had before. 19 in decimal is 10011 in binary. If I had 19 or anything that represents that number, how could I get it out? Well, what I can do is the following little trick. I can take the remainder of that number relative to 2. And that remainder actually gives me the last binary bit. It'll give me this bit right here, because that's the remainder that's left on the divide by 2. If I then take x and... Well, what I can do is the following little trick. I can take the remainder of that number relative to 2. And that remainder actually gives me the last binary bit. It'll give me this bit right here.
Oh man, the one that I just did before 19 in decimal is 100.
Because that's the remainder that's left on the divide by 2. If I then take x and divide it by 2, integer-wise, using that double slash idea, all of the bits get shifted right. That is, x double divide by 2 is now 1 times 2 to the third, rather than 2 to the fourth, plus 0 times 2 squared, rather than 2 to the third, plus 0 times 2 to the 1, rather than 2 squared, plus 1 times 2 to the 0, rather than 2 to the 1. Or another way of saying it is, notice I've taken these digits and just shifted them to the right. If I keep doing successive divisions like this, I can keep track of each of the bits that comes out, because the remainder gives me the next bit, and when I'm done with all of that, I've converted to binary form. So basic idea, given an integer, take the remainder with respect to 2, that's the low order bit, divide integer-wise by 2, shifts right, do the same thing until I've exhausted the entire integer representation. So here's a little piece of code that would do exactly that. Right? If the number's less than 0, I'm going to put on a flag that says it's negative.
This is the one I already have, right? No. Okay.
And I'm going to use the positive version of it by taking the absolute value of that number. Otherwise, I'm going to put in a flag that says it's not. And then I'm going to simply accumulate those results. If the number is equal to 0, It's just 0. That's pretty obvious. Otherwise, as long as the number is greater than 0, I'm going to do remainder, add that in because that's the next bit into result, do the division to shift it to the right, and keep going. So if I look at that, here's a simple example of doing that conversion, converting decimal to binary. I'll start with a real simple example. If I start off with number as 3 and I do that computation, it didn't print anything, but the result is sitting in result. And there I get it. The binary representation of 3 is not surprisingly 1 plus 2. Let's just check to make sure I wasn't misleading you when I said 19 was, in fact, what I claimed it was. So if I make it 19 and I run it and I look at result, it gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing. Let's take an example. 3/8 is 0.375, and in binary, that is 3 times 10 to the minus 1, plus 7 times 10 to the minus 2, plus 5 times 10 to the minus 3. It's
That's
just
so
the digits
confusing.
associated with each of the placeholders.
An internal computer representation of any number is always an approximation. I guess that's false. It's very confusing. I guess he was talking about specifically like decimals or something. Or sometimes the decimal 11 is what binary. True or false, the internal representation of the decimal number requires an infinite number of digits. I thought I just tried that, didn't I? It looks like, I mean, that's oh, wait. Oh. Why'd I put false? Whatever. I don't remember. That's it. Okay, whatever. That stuff's confusing. Oh, hey, what's up? Just saw your message. They all hit at the same time, it looked like. I am trying to learn coding, and it is not easy. It's not very easy. It was easy at first. In the very beginning, it was very easy. And then as it started going on, it started getting a little more confusing and more confusing. I'm able to hang, and I'm able to kind of grasp it. But holy crap, I mean, trying to figure out some of this stuff without, like on your own. Oh, God, this stuff's so hard, dude. It's so confusing. It's so weird. It's weird is what it is. Because it's like the idea is you're supposed to think like a computer, and a computer doesn't think like us. And so it's like, it's like you're trying to learn a foreign language that doesn't even use words. Really, I don't know how to. It's something. It's something. I don't even know how to speak a second language. So this is like, this is crazy. This is crazy.
Now that we've got an understanding of floating point numbers, now that we've got the idea of generalizing guess and check methods to do things that can do approximations, to find solutions to things, we can really start building some pretty powerful programs. We've already seen something that searches for cube roots of numbers, even if they're not a perfect cube, square roots of numbers, even if they're not a perfect square. And we've seen how we can get to quick solutions very nicely using things like bisection search. Have a great accuracy and still find good answers.
Bro, I don't know what this formula is, but this looks freaking terrifying right here. Like, what in the world? Oh my God, this is getting crazy. General approximation algorithm to find roots of a polynomial in one variable. Mother of God, bro.
I want to show you one last example, just to give you a sense of the power of computation we can now do. I'm going to stick with the idea of finding roots of things, but show you how you can actually capture things very dramatically. And that's to use a technique called Newton-Raphson. It was discovered by Sir Isaac Newton 3 or 4 centuries ago, also discovered by Raphson at about the same time. And here's the basic idea behind Newton-Raphson. It's a general approximation algorithm that's going to let us find roots of any polynomial in one variable. So that could be, for example, the polynomial like this. I've got p of x is some coefficient times x to the n plus some other coefficient times x to the n plus minus 1 and so on. And what I want to do is find the value r such that p of r is equal to 0. It's called a root. It basically is the root of this equation. Newton-Raphson will apply to any polynomial. I'm going to show you an example of using it to find square roots. And you can say, well, I already did that with bisection search.
Oh, dude, I don't even know what a... Alexa, what's a polynomial?
A polynomial is a mathematical expression with variables and coefficients, using only addition, subtraction, multiplication, and positive integer exponents. For example, 4x squared plus 3x, 7 is a polynomial with 3 terms.
Root of this equation. Newton-Raphson will apply to any polynomial. I'm going to show you an example of using it to find square roots. And you can say, well, I already did that with bisection search. You're right. But it's a nice way of looking at how we can generalize the computation. So in particular, if I want to find the square root of 24, I'm going to use the polynomial x squared equals 24. Because if I can find the value of x for which this is 0, then x is, in fact, the square root of 24. What Newton showed was that if g is a good guess to that root, then you can get an even better guess by taking g and subtracting from it the polynomial evaluated at g divided by the derivative of the polynomial evaluated at g. And if you haven't done calculus and you don't know what a derivative is, don't worry. We're going to show you what it is in this simple case of a square root. But I want to see I want to let you see the power of doing Newton-Raphson. So Newton showed if I got a good guess, I can make it better by taking p of g divided by the derivative of p at g and subtracting that off of g. So in the simple case, if I've got an equation that is some constant times x squared plus another constant, then the first derivative of c times x squared is just 2cx. So in my case of looking for square roots, x squared is plus k is the thing I'm trying to find a solution of, the derivative is just 2x. And so Newton-Raphson says, given a guess for the root, take the polynomial at that point, which is g squared minus k, take the derivative of that point, which is just 2g, take that ratio and subtract it off from g. Cool. We ought to be able to build that, and we can. It's a nice, tight, little iterative loop.
Oh my god. Okay, well,
You got this.
so, dude, you hear what he's saying here?
Yep.
Oh, this stuff just got weird, man. This is crazy. Rafts. I don't even know how to say this. Man. Okay. Raphson. Well. Holy crap. Okay. Number of guesses, so I know how many times it's going through it. 10-4, 10-4. While let's get this over. Absolute guess times guess subtract y equal to number of guesses
checking on your chat?
Yeah.
Because somebody said hello multiple times.
Yeah. No, they said it all at once.
Oh.
And then I responded to them and they didn't respond back, so. I'm probably just messing with me. Or their internet doesn't work.
Our internet's kind of slow right now, anyways.
You sure about that?
Well, maybe it's because I'm in the living room.
I can do a speed test.
Okay. Not gonna lie, I love the smell of ink.
Yeah. This is crazy. This is crazy.
Oh my god. Oh wow.
What?
It's the exam outline. Shit's getting real. Should actually be able to finish this course in 30 hours as it had suggested instead of 120 hours per course.
Alright.
It's a whole sample test. Excited and nervous, excited and nervous.
Excited and nervous.
We both end up making six figures.
That'd be nice.
Right?
Not gonna lie, this is pretty crazy stuff right here.
Yeah, your stuff is wild. I'm just learning real estate law. Like, this is a whole nother something.
Yeah.
At least real estate law doesn't change dramatically. Seems like coding does.
Well,
I mean, there is always the basics. So there's
yeah,
that.
you know when this Python program came out?
In 1995.
91.
Ah, close. Hey, it was meant to be.
So,
It was meant to
Python
be.
was,
Was born when you were born.
yeah, it's
Just
as
like
old
Mario
as me, and people are using it like crazy right now, so.
Just like Mario was born when I was born. And Luigi. Look, babe. You got this. You smart.
Man, I'm trying, man. I'm trying. I mean, remembering how to do all this stuff and use this stuff, but the math part of it's like, man, this is crazy, dude. I wonder if this will work like this. Probably not. It's okay. Where I guess it's far. Oh yeah.
More prep stuff.
works out pretty smooth. All right, all right.
So here's a nice way of generating the guesses. Again, I'm going to have some epsilon that's going to let me decide how close I am to an answer. I got the thing I'm going to look for, and my initial guess I'm just going to pick as that value divided by 2. And then here's the loop. As long as guess squared minus y, the absolute value of that is too big, I'm going to keep going. And as before, I'm going to count the number of guesses to see how long it takes. Each time around, I'm going to use that little equation from Newton-Raphson. I'm going to take g squared minus y, divide it by 2 times g, or guess, subtract that off of guess, and go back around. That's just the thing I did before. And I'm going to run through that loop until I get something close enough, and then I'm going to jump out. So let's see what happens if we do it. I've got the code over here. I'm going to load it in and run it. And in 4 guesses, it got a good solution.
I just print so much stuff.
4. Okay, it's a whole lot better than 30,000, which is where we started. With the bisection search, it was about 15 or 20. Now I've got it down to 4. Let's pick another example. Let's take my favorite example here of 54. Same thing, and I run it. And in 5 guesses, it gives me a good solution out. This is really cool. I know you don't believe it, but it really is cool because it lets me not only find cube roots and square roots, it lets me find the solution to any equation very quickly. So what we've now seen is that this idea of a guess and check method builds on reusing the same code over and over again. It takes the idea of a looping mechanism and adds to it, building into it different ways to generate the guesses and then checking to see whether I'm close enough or I want to keep going. And we've already seen now simple exhaustive enumeration, bisection search, which cuts down the amount of expense dramatically, and now, at least for root finding, Newton-Raphson, which improves it even more formally. So you've already seen 3 different...
Man, that thing is crazy. So you can find the square root of something. That's basically the... It's crazy. That's the Newton-Raphson formula.
classes of algorithms, and you've got a lot of tools for doing numerical computation.
I'm doing now. You know, I want to title this.
Well,
Huh?
1 of 6.
1 of 6.
Yeah. This is what slow success looks like.
Oh, certificate of achievement.
Now
Check
I
that out.
need 5 more.
Yeah.
We're going to come back to that as we move on through the course.
That's crazy, dude. Alright, understanding bisection learning. Find the page number. What? Okay, in this lab we will look at examples of bisection search and try to gain an intuitive understanding of how bisection search works. Imagine you are searching for a word in the dictionary. You start looking through the dictionary, but you don't want to search every page from front to back because that would take too long. You decide to look in the middle of the dictionary and figure out which half the word is in, since you know the dictionary is alphabetized. In the first example, you will see the first scenario where you know what page the word is on, but you have to find that page. In the second example, you will see the second scenario where you know what letter the word starts with and know what page each letter starts and ends on. As you click the next and back buttons, notice how the image changes and which pages of the dictionary are highlighted. As you run your cursor over the dictionaries, notice how the different page numbers are displayed in the first example and the different letters displayed in the second example represents what part of the dictionary you are pointing to. Also notice how many iterations it takes, and that's bisection search works for both page numbers. 112, 112, 112. Oh, there it is. Alright, what do we got now? 112. Next. Selected random page 42. Current maximum 80. So we got a 90. We got a 30, 35. And we got down to 157, 146. So it's literally like that number guessing game, honestly. Webster's Dictionary. Alright. Yeah, that's cool. I get it. I mean, it's basically what it did. The, using higher and lower to, well, find the number you're looking for. It's the method that they're using is what they're trying to.
Let's think about what we've been doing so far. We started introducing elements to our language. We started off with simple things, basic objects, ways to do arithmetic operations on them, ways to compare them. We introduced conditionals as a consequence of that. And we started looking at the first version of ways to actually put things together into pieces of code. So we've covered language mechanisms. We've also covered the first notion of for and while loops and therefore of iteration. And we've also seen that we could write different kinds of computations, each one in a different file that I save away on my machine so I can use when I want to do something with it. Each file contains a piece of code, and each piece of code is some sequence of operations. It could be a simple branching program, it could be an iteration like a for loop or a while loop, it could be something else. This is fine when our code consists of a few lines. This is fine when our problems are very small. But it doesn't really scale very nicely. As I start thinking about pieces of code that might be hundreds or thousands of lines long, simply doing it this way is a real challenge. It's hard to keep track of the details. It's hard to make sure that I've got the right information in the right place in that code. Does this go at line 95 or at line 296? I need a way to really capture this better. I need a way of structuring my code, structuring my computation so that I can think about it much more efficiently. And that's what we're going to introduce now. One of the things to keep in mind is, in fact, good programming is more than just adding more code. In fact, I would argue that a good programmer is measured not by the number of lines of code she's written, but by the amount of functionality that she's provided, the ability to do computations easily. And so to make that happen, we're going to take a really nice pivot, introduce a major new thing, and that's the idea of a function. We're going to describe it in a second, but the idea of a function is it's going to give me a way to encapsulate pieces of computation. And in fact, a function is intended to give me two really important aspects of computational thinking: decomposition, sometimes also called modularity, and abstraction. So what do those mean? Let me give you an analogy, something a little bit different. I'm sure you've all seen a projector. I think of a projector as a black box. Now, the one I'm showing here happens to have a black box around it, but by black box, I literally mean a construct whose details I don't understand. In fact, most of us don't know what's inside it, how it actually works. If you open it up, you see a bunch of electronics, and unless you're a really good electrical engineer, you probably don't understand how it works. It doesn't matter, because you know the interface. You know the input-output behavior. And in fact, that black box comes with a standard interface that says if I plug an appropriate piece of electronics into it, that box can communicate with it, and it's going to produce an output. It's going to show slides on the wall. That's the notion of abstraction. It's the idea that once I've built something, in this case a projector, might be a piece of code, once I've built something, I don't need to know what's inside it as long as I know how it works. So abstraction in some sense comes with a contract that says if you give me appropriate inputs, I'm going to behave in an appropriate way. That's a really nice idea. That's something that we're going to want to use, and we're going to use it with code. There's a second piece to it, and we'll stick with the projector idea. If you happen to see the opening ceremonies for the Vancouver Olympics, there was a wonderful display in which there was a huge multi-story high structure in the middle of the rink onto which images were projected. Now, it wasn't one projector, it was way too big. It was a sequence of projectors. Each of them took an input, each of them produced an output. And they all worked together in synchrony to produce that wonderful larger image. That's the second big idea, decomposition. That I can, in this case, take different devices, have them synchronized so that they work together to achieve an end goal. I want to use the same thing with code. So we're going to apply those ideas to programming. Decomposition, I'm going to break a problem up into different self-contained pieces. And once I built them, or even better, once somebody else has built one of them for me, all I need to know is what does it expect as input and what will the behavior be when it gives me an output. And the second big idea, abstraction, that I want to be able to suppress the details inside that method in order to be able to compute something using that computation. And in fact, I just said them in the wrong way. What I first described was really abstraction. Decomposition is that idea of breaking it up into smaller pieces. With those two things together, we're going to now look at how do we make programs have those two properties. Okay, inside of code, with decomposition, we're going to do the same thing we did when we talked about having multiple projectors working together. When I'm going to structure a big piece of code, I'm going to divide it up into modules. And those have the property that they're self-contained. That means they have everything they need inside of them. I'm going to use it to break the code up into pieces that I can separate apart. And they're intended to be reusable. I can use them multiple places. If you think about it, so far, even if I have a little file, I can only use it once. Or if I want to reuse it, I've got to go back and recall the file. Here I'm going to structure code so that I can use it in multiple places. And we're going to see that this idea of dividing code into modules is both going to keep the code organized and coherent. It's going to be easier to structure. Today we're going to do decomposition with functions. And in a few weeks' time, we're going to see how to do decomposition with classes. An equally powerful idea. We're going to suppress details with abstraction. Again, I said with the projector, I don't need to know what's inside, I just need to know what it does. In programming, we're also going to think of a piece of code as a black box. I don't need to see the details inside once I've written it, or especially if somebody else has written it for me. I, in fact, don't want to see the details inside. What I simply want to know is that it's going to work the way it was advertised. And we're going to achieve abstraction with something called a function specification or a docstring. And in a second, we're going to see examples of both of those. But there's the idea. Abstraction, decomposition. Two powerful ideas that we want to capture inside of computation. One of the things that comes out of this is not only do they work well together, but they can then be used many times. And in fact, not only can they be used many times, I only have to debug it once. It's one piece of code. If I want to make a change to it, I change that piece of code. Anything else that depends on that code will inherit that behavior because they simply depend on that code. So how do we create this notion of abstraction and decomposition in Python, or actually in any programming language? And the answer is we introduced the idea of a reusable piece of code or a chunk of code called a function. Functions are not going to be run in a program until we actually ask them to do that. So as opposed to things I was typing into my shell, every time I typed in an expression, it was invoked or evaluated, I'm going to create a definition of a function, and when I read that in, it's simply going to create the ability to do that computation, but not actually call it. And we'll see an example of that in a second. What are the characteristics of a function? Several. First, it has a name. That makes sense. I've got to be able to refer to it in the same way that I had a variable as a name for a value. A function will have a name. It will also take a set of parameters. These are arguments or values that I'm going to use inside the function when I do a computation. It's going to make sense in a second when we look at an example. Every function has to have parameters, but the number of parameters could be 0. Or it's a funny way of saying it's going to take in a parameter list, but in fact it may need no parameters, and I'm going to decide when I create a function how many parameters I need. We'd like every function to have a docstring. That is a documentation that tells me what the function does. We'll see an example of that in a second. And finally, a function has a body. And the body is the sequence of commands or instructions that we want to actually have happen when we use the function. Those are a lot of words. Let's look at an example to get a sense of this. Here's a definition of a function, and I'm going to walk through each of these pieces. So, the first part of it is I've got a keyword, in this case def. And it is a keyword, meaning it's a special symbol to Python that tells me I'm about to define something. In this case, I'm about to define a function. That is followed by a string that is the name of the function. In this case, it's is_even or is_even. That's the name of the function I'm going to give, the name I'm going to give to this function. That is followed in parentheses, in those parens, by 0, 1, or more parameters. In this case, I've got 1. And I'm giving it a name. Think of it like a variable name. I'm saying I'm going to use the name I as the name for a parameter inside this function. And that's then followed by a colon to tell me I'm done with the top line of the definition. I'm about to follow it with other information. So keyword def, a name, and in parens, some number of parameters. Immediately below that, in triple double quotes, which is a wonderful expression, is a docstring. It's up to you how to use this, but traditionally you would specify what's the input to this function and what's the output of this function. It's a little bit like a contract. In this case, I'm saying I'm expecting one input, I'm calling it I, and it's a positive integer. And what I'm going to return is true if I is even, otherwise I'm going to return false. As we'll see in a little bit, one of the nice things about a docstring is, once I've defined this function, if I go to call it, which I'm going to get to in a second, Python will automatically bring up a little window that tells me the docstring, that reminds me what the conditions for this function are, which is great. So, keyword, name, parameters, I've got a docstring. Immediately below that is the body of the function. This is the sequence of commands or expressions I want to evaluate when I'm ready to use this. Notice the indentation. All of this is indented here. This is telling me where the body of the function is. And in fact, it will be everything until I get back to something that returns to the left-hand side of the editor or of the shell. In this case, I've got two expressions in my body. It's going to print out simply the string I, and then it's going to return a value. We'll come back to the return in a second. There's how I write a function. Now, how do I use it? The function has a name. The same way I could use a variable as a name inside of an expression, I can use the function name. And in particular, later on in the code, I can say an expression like is_even, and then an open paren, followed by an expression whose value I'm going to use inside of that procedure, followed in this case by a closed paren because there's only one parameter. I call this invoking or calling the function. I'm using the function. We're going to look at some examples in a second, but the basic idea here is that when I call this function, I'm going to take the value 3 in this case, and everywhere I see an I in the body of the function, I'm going to use that value in place of I. And in fact, if I look at it then, inside of this particular expression. I'm going to print out simply the string high. And then I'm going to evaluate this particular expression. And it has the keyword return followed by an actual value. Now, I just said, in this case, if I've called is_even with the parameter 3, I now holds the value 3. So I'm going to evaluate 3 remainder 2 and say, is that equal to 0?
False.
In this case, it's not because the remainder is 1. And I'm going to then return that value to whoever called this function. So that's the expression I want to evaluate and actually return. So it returns a keyword that tells me I'm ready to stop the computation, and whatever the following expression is, that is the value I'm going to give back to the person who asked for it. In this case, it was simply at my shell. But we'll see in a second, it could be somebody else that's going to use it as part of another computation.
Yeah, I already learned this part. Estimated time. Function types for each type of return. Indicate the type of output that the function A will yield. If you put A in well, see, I haven't seen it used like this, though. This is kind of the parentheses on top and bottom. I mean, it's are they asking about the A right here? I mean, but that's not the input. This is the input. That's just the name of the function. Like, what's the name of the function that you're going to call? Oh, I mean, I guess if you call the function by typing A, what is it going to do? I mean, if you don't give it a value, then, or I guess it's that if it uses X, then integer or float, I mean, it's return X plus 1. I mean, that'll turn it into an integer. Oh, that'll be a float. Return X plus Y. What it'll yield. I don't think you can use an integer float to be a boolean. This won't be a float. What, an integer? If this is an integer, it's gotta be a float, right? And this is no. Huh. Return X plus 1. Oh, I don't know. Number, I guess. Is that? Okay. This is. No. Yes. I already tried integer. couldn't be a boolean. Man, what the fuck? It's a non-type? What the how does that work? Let me see. X, Y. 10-4. Okay. Parameters. Okay. X. Float. Oh, is it because there's a period in there? Okay. Then X plus Y taking me 2. What is this? It does nothing. But that's because of the period, right? Missing 2 required positional argument. I mean, see, that's what I'm saying. That's why I don't understand what this is supposed to do. Oh, they all got periods except for the last one. Okay, let's do F. 9. Nothing. Okay. Type. Jesus. Non-type. This is weird. Okay. Let's try the number. Let's see. C. 10-4. X. Y. This is weird. Blah, blah, blah. Bah. Parameters. Why does it do all this? See, this like, you know what I'm saying? I don't need all of this. See, I'm just like, okay. X. Y. Into a float. Return X plus Y. Unexpected what? What do you want? Gotta have it at the perfect little spot. Okay. Type. C. Okay. Float is what it says there. see. 5, 6, integer. Okay. What the is this? Num. What is num? It's a text. It does nothing. It's what is this? What? Okay. I don't know. Write a Python function square that takes one number and returns the square of that number. This function takes in one number and returns one number. Okay, so easy enough. Your code here. Look, mates, this is how you do it, alright? If I want to square something, I just literally x equals x, blah blah, chika, right? And then we'll return x. I know I'm correct. That was easy peasy, bro. Easy peasy. How are the last ones so difficult? And this one's like, eh, whatever. I'm just saying. That was ridiculously easy. I was probably about to get a crazy complicating though. Write a Python function eval quadratic abcx that returns the values of the quadratic a times x squared plus b times x plus c. This function takes in 4 numbers and returns a single number. Bro. You put the thing right here. Like, that's all I... What the... That's okay, fine. You're gonna make me type it? Oh, that's fine. Type this shit. Jesus. It's like 8 times x da 10 4 plus b times x plus c. Right. And what is this going to equal? You know, I can call it whatever I want to call it. I can call it but. And then return but.
Knock over my computer.
Error. Oh no. Line 7. It doesn't like the but word.
Hey, I'm not playing this game.
Here, let's just do this. Just. I don't even gotta do all that. Incorrect. God damn. I messed up. Okay. It's fine. It's fine. I put it in the wrong order. Either way, you're returning the but. Okay. Let's see. Video calling functions in scope. Return versus print. Return gives you the command. Print can be used outside functions. Return only has meaning inside a function. Only one return executed inside a function. Code inside a function, but after return statement, not executed. Has a value associated with it given to function caller. Print can be used outside functions. Can execute many print statements inside a function. Code inside function can be executed after a print statement. Has value associated with it. Outputted to the console. Well, it just got easier. It was like really, 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 really hard for a second there,
Yeah.
and then it got really, 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 really easy.
That's promising.
Well, because
You
he's
understand
teaching. Well, no, he's teaching another thing that's I already know how to do. So defining a function.
that. Defining a function.
Yeah, when I was doing that dev thing, the other website, they taught me that first day I was messing with it. I already know how to do it.
Are you gonna get the kids today?
Me?
Yeah.
I can.
That'd be awesome.
That'd be awesome. What time is it?
2:15.
23.
2:23.
Yep.
There you go.
2:23. You gonna patch up my pants for me? I told you this I was gonna rip.
Oh my god.
I got a
Ripped
big
it.
old
Yes,
hole.
I will patch up your pants again for you.
I told you it was gonna happen. Okay.
The idea of function invocation, function calling, is really important. It's central to how we're going to use functions to control our code. So I want to work through in a little more careful detail exactly what happens when we call a function and how we get values associated with variables.
That's pretty simple.
You'll see on the screen here I've got a little piece of code. I'm defining a function called f. I'm binding x to 3, and then I'm going to call f with the value of x and bind that to z. Let me show you what happens if I actually run this. So on my computer, I've got a version of that file, and I'm going to load it into my shell.
I already know. This doesn't kick in until you call it. The function, the defining function, is just a defining function. It doesn't happen until you call it. When you call it, it happens. Now, x equals 3 is the first thing that happens. X now equals 3. X is now a variable for the integer 3. Z equals f with the x in parentheses. X is the integer g that returns to the defining function. You have called the function saying that z equals this function, and now 3 is going to be x. 3 equals 3 plus 1. Print in f. Actually, I don't know how that one will turn. Oh yeah, the way so it'll print that, and it'll say in f parentheses x parentheses semicolon x equals, God, so many words, and then it's gonna give you that variable which is going to be 4. So when you put z equals f with the x, what it's going to do is z is going to equal the function. So when you hit z, it is going to print in that, and it's going to say it is the x is 4. And if you do it again and again and again, the number's going to keep going up.
And what it prints out, as you can see, is it says in f of
See if I'm
x,
right.
x is equal to 4. How'd that happen? What's going on here? Because x seems like it's used in a lot of places. So this is going to be an important opportunity to look at how functions are called. As I've already, what's going on here? In f of x, x is equal to 4.
There it is.
How'd that happen? What's going on here? Because x seems like it's used in a
going on
lot
here?
of places. So this is going to be an important opportunity to look at how functions are called. As I've already said, the key idea is each formal parameter, in this case I only have one, is going to get bound to the value of the actual parameter when the function is called. And then when I call a function, I'm going to create a new environment, sometimes called a frame or a scope, a new place in which I'm going to bind variables and relative to which I'm going to evaluate the body of the function. Think of that scope as a mapping of names to objects. And in fact, we've been using that idea. When we were just talking to the shell, when we defined x to have a value of, say, of 5, we were creating in the global scope or frame a binding of the name x to the value 5. Now, let's look at this in a little more careful detail. imagine I now do what I just did on my computer. I evaluate this sequence of expressions. There's that formal parameter. There's the actual parameter I'm going to use. And let's look at what happens. I evaluate that, and in that global frame, I create a set of bindings. First one is, evaluating that definition binds the variable name f to something. Oh, but that's important, because that something is just a set of code. I haven't run f yet. I haven't tried to do x equals x plus 1 or anything else. I've literally, in the machine, said, associate the name f with a chunk of stuff. Next thing I did was I evaluated x equal 3, and that just creates a binding. We've seen this before. So in the global scope, x has a binding to the value of 3. And now I'm ready to evaluate that last expression, which says give the name z the value of calling f on x. And I'm ready to do that. Now remember, before I can actually do the binding of c, I have to get the value of that expression. So calling f literally creates a new scope, a new frame. It will actually inherit things from the global frame if it needs it, but right now I've got a new environment. The definition of x has a formal variable x, and that's exactly what that corresponds to. And the value associated with it is the value of x that I passed in, which actually came from there. I know it looks a little confusing. I'm deliberately using two different values of x so you can see where the bindings come from. So f evaluated on x says, what is the value of x? I get it from the binding that I just previously. So inside that f scope, x is bound to 3. Now, relative to that scope, I'm going to evaluate the body of f. I want to do the work that f says it's going to do. So let me see what happens there. First expression says, evaluate x plus 1, and I'm actually going to go back for a second. Remember, in the f scope, x has the binding of 3. I add 3 plus 1, that's 4, and I create a new binding for x, but in the f scope, because that's where I'm doing the work. So it changes it here. It does not change the thing that was out in the global frame. That's great. Now, relative to that, I'm going to print out something, and on my computer screen, you saw it said, in f of x, x is equal to, the value of x in the f scope, and that's why it printed out 4. And then what it's going to do is it's going to return x. So literally it's going to get the value of x in the f scope, which is 4, and it's going to return it to the person who asked for it. And what was that person? That was down here. We're doing the binding of z. So I've just returned to that binding a value for f of x, which is 4, and that creates the binding for z. If this is a little confusing, watch the same segment again, because this is an important idea. Anytime I do an rephrase that. Anytime I do an invocation of a function, I create a new frame. I bind the formal parameter of that function, or parameters if there's more than one, to the values of the expressions passed in, and relative to that frame, I now evaluate the body of that expression. When I'm done with the body of the function, if there's a return, I'm going to send the value back to whoever called for it, and erase or remove that frame because I no longer need it. Okay. With that idea, let's look at a couple of other examples. First, what happens if there's no return statement? Here's my function from before, is even. But rather than returning is the remainder of I divided by 2 equal to 0, I just have the expression. So there's no return here. What happens in this case is that Python returns the value none, because I did not give a return. So Python will say in a function call, if you don't have an explicit return, I return the none value. It represents the absence of a value, and unfortunately that would mean in this case I would not get back the answer of true or false. I would simply print out nothing, because there's nothing to be returned. Point of this is, anytime I want a function to do something, unless it's simply doing something we call a side effect, I always want to have at least one return that's going to give a value back. So remember to keep your returns in. In fact, that gives me a chance to talk about the difference between return and print. You can see the description here, and let's just do it quickly. Return only has a meaning inside a function. It's the only place we can use it, inside a function. I could have more than one return. If I have branches or other conditionals, I might have different places from which I want to return, but only one return will ever be executed inside the function, because it's going to throw me outside of the function and return a value. Any code inside the function but after the return statement will never be executed. And of course, a return does have a value associated with it. It's given back to the person who called the function. By comparison, while return has a meaning only inside a function, a print can certainly be used inside a function, but it can also be used outside of a function. We've already seen that. We can also execute many print statements inside a function, and any code inside the function after that print statement can, in fact, be executed. Again, a print has a value associated with it, but it is simply output directly onto the console rather than being returned. So prints are going to be handy to have us pass information back to the user to let them know the status of a computation. Return is the way in which I'm going to get a value back to somebody who asked for it, whether it's me as the user or some other function call. With that in mind, let's look at, in fact, how you might have other function calls. So, not only can parameters have numerical values, they could also have other values, including being a function. So I have three definitions of functions here. The first one, A, takes no parameters. I've said this earlier, but I'm going to say it again. Notice it has an open and close param. That's important. I have to tell it that there are no parameters there. Function B takes one parameter, in this case called y, and function C also takes one parameter. In this case, it's z. What's interesting about this is how these functions are going to use them, and in a second I'm going to run it, but notice I'm going to call function A with no parameters, so an open close paren to tell me there are no parameters. I'm going to call function B. It's going to take in one parameter. In this case, I'm going to give it a number. And function C is going to take in one parameter, but in this case, it's another function. Whoa, that's funky. It's actually okay. I can pass in the name of the function, and that will literally pass the actual function in to that parameter call for function C. Let's see what happens if we try this. So I've got that code loaded up over here. I'm going to pass it into my computer. And notice what it printed out. The first thing is it printed out inside function A. That came from calling this function, and that's the print statement right there. There is no return in function A. And so in fact, the print takes the value returned by function A, which was none, and it printed it out on my computer. I then take the next call. I pass in 2 to function B. Function B prints inside function B, right there, which is the next thing it did. And then it returns the value passed in, which is the value of y, which is 2. That gets added to 5, which is why on my machine I printed out 7. The print statement printed out 7. And then the last one, again, a little funky. I passed in function A as an argument for z in function C. And what happened? It printed out inside function C, and then it called a return of calling z with no arguments. And what's z? It's function A. Oh, that's nice, because function A then said print out inside function A, which it did. Return nothing, because there is no return statement, and so this print at the bottom then printed out none. We could step through it more carefully, but you hopefully get the idea. In each case, I'm simply evaluating the body with respect to a frame. And the arguments could in fact be other functions that I can invoke inside of a function call, which I did inside of function C. So, as a consequence, inside of a function, we can both access a variable defined outside as well as a variable defined inside. On the other hand, inside of a function, we can't modify a variable that's defined outside of the scope of that function. And here I have 3 little examples just to give you a sense of that. What I'm going to do is show you basically what would happen for each one of these function calls. So I've defined f of x to be set x equal to 1, add 1 to x, and then print out the value of x. I've defined g to simply say print x, and then print x plus 1. And I've defined h to have a body that says simply increment x by 1. And I want to think about what do those things actually do. Well, let's look at the first each of those examples. In each case, I'm going to define x to have the value of 5. I'm going to call the function with that value of x, and then I'm going to print out x. What happens? In the case of f of x as 5 is passed in. I read.
Oh, this shouldn't interfere with this because oh wait, yeah, no, oh yeah, it's got it right here. 5 becomes this x becomes this y, this y. Wait a second. X equals 1. But I think this x only exists within here.
We define x to be 1 inside of there. And then I add 1 to that value of x, which is 2. And then I print out x. So in fact, f of x is going to print out the value 2. And then this print statement is going to print out the value 5. Why? Because it sees the value of x defined in the global scope, which is where I am. What happens with the case of g? G says, well, first of all, I call g with the value of x, which is 5, which means 5 is going to be used in place of y. And then I say print x. You say, wait a minute, there is no x as a parameter to g. That's fine, because it then says if I can't find it in the frame associated with g, let me look outside. And there is a value, which is 5. So in this case, it's going to print 5. Then it's going to print 6, which is x plus 1. It has no return, so it's not...
Wait, hold on. X equals... Two and 5. Now, why does it do 2 and 5? Because the function happens first. So, I see we have this here. X equals 5. 5 becomes x here. X becomes y here. Now, y does not exist in this function. So, I don't know if he mentioned this. It is redefined here as 1. But even putting x within here does not matter, and I think that's kind of because this x exists as an integer of 5, which turns this y as an integer of 5, but does not interfere with this because this is not y. If this was y, then that 5 would be carried here. Even though this would override it. If this was y, it would override it. But even then, like, that's the thing, like, there is no y here. So even then you're gonna have the same outcome. Local variable x. Oh yeah, I have to put a... Yeah, because look, if I hit play, there's no value to x here. So I have to create a value to x, because in here, there is no value. X equals 5 on the outside, not on the inside. Y on the inside will equal 5. But this isn't printing y. This is printing x. If I change this to y, for example, none of this crap matters, because that doesn't have to do anything with any of this, and it will print out 5 2 times. Yep. I don't know why now. I'm surprised they didn't mention that, because that's not even going to interfere with that. I mean,
call. So I've defined f of x to be set x equal to 1, add 1 to x, and then print out the value of x. I've defined g to simply say print x, and then print x plus 1. And I've defined h to have a body that says simply increment x by 1. And I want to think about what do those things actually do. Well, let's look at the first each of those examples. In each case, I'm going to define x to have the value of 5. I'm going to call the function with that value of x, and then I'm going to print out x. What happens? In the case of f of x as 5 is passed in. I redefine x to be 1.
Oh, is it time?
Yeah.
All right. Heading out.
Bye.
I don't even think